More than 13 billion years ago, the cosmos looked nothing like the universe we see today. The first stars were beginning to ignite, the earliest galaxies were taking shape, and the familiar worlds of the modern universe had not yet appeared. Yet observations from the James Webb Space Telescope have revealed signs of a powerful object active during this astonishingly young era. The object, identified in the source as QS01, is associated with a rapidly moving reservoir of gas surrounding a supermassive black hole. The estimated black hole mass is about 50 million times the mass of the Sun, even though the universe was only roughly 700 million years old when the light we see today began its journey. On a cosmic timescale, that is remarkably early. What makes the observation especially important is that Webb did more than detect a faint ancient source. By examining the light from the gas around the central object, astronomers could study how that material was moving. Spectroscopy separates light into wavelengths, and motion changes the position of spectral features through the Doppler effect. Those shifts provide a way to reconstruct the gas dynamics and estimate the mass of the hidden object controlling the system. This creates a major question about the relationship between black holes and the first galaxies. The traditional picture is that galaxies assemble, stars form inside them, stellar remnants create black holes, and some of those black holes eventually grow into supermassive objects. But the early universe did not have much time for a small black hole to grow into something as massive as the object associated with QS01. One possibility is that some of the earliest black holes began with unusually large seeds. In the young universe, enormous clouds of mostly hydrogen and helium could have collapsed under gravity. Under certain conditions, material might have formed a massive black hole seed directly instead of passing through the ordinary sequence of stellar birth and death. Such a seed could then accrete gas and grow rapidly. If that scenario is correct, the order of events may have been different from the simple picture we often imagine. Rather than a fully developed galaxy producing a giant black hole at its center, an early massive black hole could have become one of the dominant gravitational structures first, with surrounding gas and stars later assembling into the galaxy around it. The motion of the gas is crucial evidence because it shows that this is not merely a random cloud floating through ancient space. The material follows an organized pattern influenced by a powerful gravitational source. Webb can examine its velocity, chemical signatures, and changing properties across the distant object, allowing astronomers to reconstruct a system that existed more than 13 billion years ago. The environment also appears remarkably primitive. Much of the gas is made from the light elements expected in the early cosmos, while heavier elements produced by earlier generations of stars are less prominent. That combination is striking. An apparently young environment containing a black hole that had already reached an enormous mass. Still, this discovery does not provide a final answer to the origin of the first supermassive black holes. It is evidence that can be used to test competing explanations. Direct collapse, unusually heavy early seeds, primordial processes, or several mechanisms working together could all play a role. More observations are needed to determine which explanation best matches nature. What makes QS01 so compelling is therefore not simply its age or its size. It gives astronomers a glimpse of a period when the first large cosmic structures were being assembled. By measuring ancient light and the motion encoded within it, Webb is allowing scientists to test ideas about how galaxies and black holes grew at the beginning of cosmic history. The deeper Webb looks, the farther back in time it can observe. More objects from this era may reveal additional massive black holes, developing galaxies, and unusual gas systems. Each discovery can add another piece to the puzzle and may show whether QS01 is an exceptional case or part of a much larger pattern. When we look into the distant universe, we are also looking into its history. Every photon has traveled across immense stretches of expanding space before reaching our telescopes. Sometimes those ancient photons carry evidence that forces us to rethink a story we thought we understood. QSO the first of may be one of those clues. A glimpse of a black hole, moving gas, and a galaxy caught during one of the earliest chapters of cosmic evolution. The mystery remains open. Perhaps the first galaxies grew around enormous black holes. Perhaps several different processes shaped the earliest structures. Or perhaps future observations will reveal an explanation we have not yet considered. For now, Webb has shown us something extraordinary. In a universe only a fraction of its present age, something massive was already moving, feeding, and shaping its surroundings. And that is the real significance of the discovery. The ancient universe is not simply a static photograph of the past. It is a record of motion, growth, and transformation. The more clearly we can read that record, the closer we come to understanding how the first galaxies and black holes became the cosmic structures we see today. The mystery deepens. The discovery of QSO-1 raises a much bigger question than simply how a black hole could become so massive so early. It forces us to reconsider the sequence in which the first major structures of the universe appeared. For years, astronomers often pictured galaxies as the main structures that came first. Gas collected under gravity, stars were born, galaxies grew, and black holes at their centers gradually became larger. But the earliest universe may have followed a much more complicated path. A massive black hole seed could have changed its surroundings from the beginning. As gas fell inward, enormous amounts of energy could have been released. The growing black hole would have influenced nearby gas, affected star formation, and helped determine how material was distributed around it. In that sense, the black hole may not have simply been a passenger inside a young galaxy. It may have been an active force in the galaxy's development. This is why the gas detected around QSO-1 is so important. Its movement gives astronomers a way to study the invisible central object indirectly. The black hole itself cannot be photographed like an ordinary star because light cannot escape from inside its event horizon. Instead, scientists study the material responding to its gravity. The technique is remarkably powerful. Light from the distant system contains information about the atoms in the gas. When that gas moves, its spectral features shift. By comparing those shifts across different parts of the object, researchers can determine how the material is moving and use that information to estimate the gravitational mass at the center. Imagine watching water circulate around a drain without being able to see the drain itself. The pattern of the water tells you where the drain is and how strongly it is affecting the surrounding flow. In a similar way, the motion of ancient gas reveals the presence and influence of an invisible black hole. The measurements associated with QSO-1 suggest a system dominated by a black hole with an estimated mass of roughly 50 million suns. That is extraordinary for an object whose light comes from a period when the universe was only around 700 million years old. The real puzzle is the amount of growth required. A normal stellar remnant black hole begins with a relatively small mass. Even with continuous feeding, turning such a seed into a monster containing tens of millions of solar masses in the available time is extremely difficult. This is one reason astronomers investigate the possibility of heavier starting seeds. One proposed route is direct gravitational collapse. Under special conditions, a huge cloud of primordial gas might avoid breaking apart into ordinary stars and instead collapse toward a massive central object. Such a process could create a black hole seed far larger than the remnants produced by individual stars. Another possibility is that several growth mechanisms operated together. Early black holes may have merged with one another while simultaneously consuming surrounding gas. Dense environments could have accelerated that process. The young universe may therefore have produced several different pathways toward supermassive black holes. QSO-1 does not, by itself, determine which explanation is correct. What it does provide is a valuable test case. If similar objects are found at comparable ages, astronomers can begin to determine whether unusually massive early black holes were common or whether QS01 represents an unusual event. The story also connects to the mysterious population known as little red dots. These compact, distant objects became one of Webb's unexpected discoveries in the early universe. Some appeared to contain rapidly growing black holes, and understanding their true nature may help explain how massive black holes became so common so quickly. There is another important clue in the chemistry of the surrounding material. The early universe was dominated by hydrogen and helium. Heavier elements had to be manufactured inside stars and spread into space through later generations of stellar activity. Finding a massive black hole in an environment that still appears chemically primitive creates a striking contrast. It is almost as if the central object had matured faster than the environment around it. That contrast may eventually tell scientists something about the earliest stages of galaxy formation. If black holes could become massive before their host galaxies fully developed, then the relationship between galaxies and their central black holes may have been established very early. Perhaps the first galaxies were not simply factories that built black holes. Perhaps some black holes helped organize the material from which those galaxies grew. That possibility changes the question from, how did galaxies create their black holes, to a much more complicated question. How did black holes and galaxies grow together from the beginning? Future Webb observations could be decisive. By finding more ancient systems and measuring the motion and chemistry of their gas, astronomers can compare different environments and look for repeating patterns. If many young galaxies contain disproportionately massive black holes, the heavy seed idea becomes increasingly interesting. If instead most early galaxies show a different relationship, scientists may need to search for another explanation.